Now let us talk about the more familiar power series, that is the Taylor series. Okay, and in addition to the Taylor series, in this section we will also talk about the singular points and analyticity. You may be already knowing what analyticity means from the theory of, well, calculus of complex variables. Okay, so how do we define Taylor series of a function about the center x0? We define it as follows. Taylor series of the function f centered at x0 is given by summation as n runs from 0 to infinity. Coefficients are the nth derivatives of the function at x0 upon n factorial and into the standard term, that is x minus x0 to the power n. Okay, and assuming that it is not a useless series, the interval of convergence is given by mod of x minus x0 less than r. Okay, and r not equal to 0. Okay, now we are going to define a few things. Okay, in particular the singular point and the analyticity. Point number 1. If we are given that the Taylor series exists and converges to f of x at x equal to x0, then f of x is said to be analytic at x equal to x0. Now you may say, what does the second point mean? We are under the impression that if at all the Taylor series of a function converges, it has to converge to f of x, don't we? Okay, but now I will show you with example that this may not always be true. Okay, meaning if the Taylor series of the function f at x0 converges, okay, if the convergence is ensured, it may converge to f of x or it may not converge to f of x. Okay, now this second point is a bit counterintuitive. Okay, but we will not encounter any of the problems based on that, but nonetheless it is very essential to know the proper definition of analyticity. Okay, so when do we call a function analytic at x equal to x0? 2 points. First, the Taylor series should exist, so it is a necessary condition, and second thing, it has to converge to f of x at x equal to x0. Okay, what are the examples of analytic functions? Polynomials, of course, the exponential function e to the power x, and the trigonometric functions sin x and cos s, which are analytic everywhere. Now in the theory of functions of single complex variable, if we have a function which is analytic everywhere on the complex plane, like e to the power x, we call such functions as entire functions. Okay, fine. See, that means if the function is defined at a point, it may not ensure that the function is analytic at that point. Okay, examples are root x. Now you'll say, okay, root x is defined at 0, so why will we not call it analytic at x equal to 0? Okay, you observe that its Taylor series about 0 is non-existent because the first derivative of root x is 1 upon 2 root x, and this is not defined at x equal to 0. Okay, so this is not an analytic function at x equal to 0. Okay, not analytic. Now if f of x is not analytic at x equal to x0, then what do we call that particular function as? We call the function to be singular. Okay, examples root x, the one that we discussed. Now for x to the power 4 by 3, the first derivative is defined, okay, because the power of x there will be 1 upon 3. But all the subsequent powers of x, okay, or hence the derivatives will not be defined due to negative fractional powers of x, okay, which are not defined at 0. Okay, The function tan x is or has a singular point at x equal to pi by 2 because the function itself is not defined at pi by 2. Okay. Now, although we say singular point, points are never singular. Okay, the function is singular. Okay, but usually we use the terminology or the term singular point. Okay, so if f is not analytic at x naught, that particular point is known as singular point. Okay, and later on we are going to see the classification within the singular points, and the method of Frobenius that we are going to see later is applicable to something that we call regular singular points. But if you don't know what singular points are, it will not make sense to you what regular singular points are. Okay, that is the purpose of this discussion. Okay, singularity has something to do with the Taylor series or the Taylor series of the function, and there are two conditions, okay, for it to be called as analytic. Okay, let me now present to you the example confirming the existence of at least one function where the Taylor series exists, but it doesn't, it is convergent but doesn't converge to f of x. Okay, so this is what is really weird. We have a convergent Taylor series, but it doesn't converge to f of x. Okay, so we consider this function. If x is less than or equal to 0, then the function is equal to 0, and the function is given by e to the power negative 1 upon x if x is greater than 0. Okay, now you may see that the Taylor series of this function at x equal to 0, which is essentially its Maclaurin's expansion, this converges to 0 everywhere. Okay, meaning the coefficients are 0 or the derivatives, and therefore it actually fails to converge to e to the power minus 1 upon x for values of x which are greater than 0. Okay, because we know that this is not a constant function. Okay, it is given by e to the power minus 1 upon x if x is greater than 0. But if you use the formula for Taylor series mentioned here, okay, you will find that the series converges, the Taylor series, but it converges to 0 everywhere. Okay, we would like it to converge to 0 for negative non-positive values of x, but we would not like it to converge to 0 for positive values of x. Yes. Okay, so although the Taylor series converges, it fails to converge to e to the power minus 1 upon x for positive values of x. However, as far as our examples are concerned, we will hardly see such functions. So what is our way of checking analyticity? We will simply check for existence of derivatives of all order, including the fact that the function itself is defined at that point. Okay, which means the examples that we discussed here, root x, x to the power 4 by 3, these were not analytic at 0 because the derivatives, the higher order derivatives were not defined at 0, and tan x is not analytic or singular at pi by 2 because the function itself is not defined. Forget about the derivatives. Okay, so this is now the groundwork which will actually help us in understanding the way we solve differential equations of second order by the power series method in a better way. Okay, so this is the end of this section.